In this tutorial, you learn how to read audio signals from a microphone amplifier with a microcontroller to make your designs reactive to sound. In the description below the video, you will find a link to a GitHub repository that includes a wiring schematic, the bill of materials, and detailed explanations for each line of code. But first of all, let's have a look at a bit of theory. Physically, sound is a vibration that travels through a transmissive medium as an acoustic wave. Sound waves are rapid changes of pressure and particle velocity, and music, speech or noise are complex superpositions of sinusoidal sound waves. The amplitude of a sound wave determines its volume, and the frequency determines its pitch. In this tutorial, we are concerned with the amplitude, the volume or loudness. Loudspeaker cones or headphone diaphragms move air molecules backwards and forwards. A plotted audio waveform looks symmetrical, and the volume at any moment depends on both positive and negative domains, on the peak-to-peak level. At the zero crossing, the pressure and volume are zero. That's also where you want to cut and splice your samples when editing music. The audio signal from a microphone amplifier is a voltage that we can sample with a microcontroller's analog-to-digital converter, ADC. We sample the audio signal at a fixed frequency, but it will never correlate with the irregularly occurring peaks of the waveform. If the sampling frequency or the bit depth are too low, we can't capture enough information about the sound wave's shape. If we raise the sampling frequency and bit depth, we'll capture more information. See the effect that simply doubling the frequency and only one extra bit have on the quality of the data the ADC generates. By default, the audio signal fluctuates around 0 volts. This is why the signal must be conditioned electronically and then in code. At the standard 5 volts, the silence level of 0 volts is offset to 2.5 volts by the microphone amplifier circuitry. However, all the positive and negative peaks, that means all the loud parts, are now above 0 volts. And how do we know where the silent zero crossings are? Therefore, we flip the negative half of the signal upwards, a method known as full-wave rectification, and we capture the loudness only with positive peaks. This means that an ADC return value of 512 means silence, and everything goes up from there. We also refit the value range so it starts at 0 instead of 512. There's still an issue though. The values we get from the ADC don't use the full available range from 0 to 512. Stretching the range with a map function in code won't help, because values that weren't sampled by the ADC in the first place won't magically appear out of nowhere. The good thing is that most low-cost microphone amplifier boards do the first part of the job for us. Unlike for headphone jack or line-level inputs, we don't need an extra circuit to bias the output. The microphone signal is added or subtracted to or from the offset. A tiny trim potentiometer on the back of the board allows you to set the level of signal amplification, the gain. If you are working with rather quiet sounds, please be aware that with a higher gain, the circuit's own noise will also be amplified. To keep it simple, we keep hardware to a minimum, because the clever stuff happens as always in the code. Here's an overview of all parts in case you're not so familiar with them. You'll need the specified components, but you can find cheaper substitutes online. The wiring of the two setups is very straightforward. So, let's look at the different options. In the standard setup, we power the microcontroller from a 5V PSU and the microphone amplifier board from the microcontroller's 3.3V output. We also wire the output to the analog reference pin and set AREF to external encode before the first analog read instruction. In the improved setup, we filter the PSU's 5V output to the microcontroller with two capacitors. We use two low-tolerance resistors as a voltage divider for a lower analog reference voltage of 2.5. You can also search for two identical regular resistors with a DMM. We power the microphone amplifier board from the microcontroller's 3.3V output as before, but filter the input with an RC circuit, a resistor and a capacitor. For working with stereo, just add a second microphone amplifier board to another analog pin. Now we have something to examine the signal quality and range. In a for loop without other instructions, we read 512 samples as fast as possible and only then print the values to the serial plotter window. Leaving the default ADC prescaler value of 128 unchanged, it takes 56 milliseconds to read the samples. With a lower ADC prescaler of 64, it takes 28 milliseconds, and with 32, it only takes 14. That means we have a sampling frequency of over 36 kHz, so we better use this setting later. Like for any kind of audio equipment testing, we sample a 1 kHz sine wave from a tone generator. It's obvious that solution 2 delivers the best signal quality and amplitude, certainly good enough for most purposes, while solution 1 is noisier. The default 5 and 3.3V approaches are so noisy that they are not even worth considering. While version 1 is okay, the improved version 2 delivers the best resolution because the audio input will generate a much larger range of ADC values. So, apart from using the improved input circuit we looked at, we only need a few lines of code. First, we declare a few constant and changing variables. In setup, we set the analog reference voltage to external, and we must do so before using the analog read command. Also, don't upload code with the external setting if you are using the AREF pin. To sample at a speed of 36 kHz instead of the default 9, we set the ADC's prescaler to 32. In loop, we first take the time, and then sample and rectify the raw audio signal until 30 milliseconds are over, while finding the minimum and maximum values within that period. It could be that a small correction factor is necessary to bias the audio signal exactly. Finally, we chart the values in the serial plotter window. With no sound, audio in RAW should deliver a steady value. However, even when tested in a soundproofed cabin and with power supply filtering, the microphone amplifier isn't noise-free. After all, this thing is no high-end product. Let's compare the real-world results. With a sound clip at full volume, let's see the values from both setups. Please try to remember the shape of the original waveform. When we compare the serial plots of raw and rectified values, it's obvious that version 2 delivers the best peak-to-peak amplitude. The maximum value in each sampling period captures the beat structure and dynamics, and the 2.5V approach delivers a much higher resolution. Now we can do interesting stuff with the audio data, for example having motors, actuators or LEDs react to music, speech or noise. We'll look into that in another tutorial. And now it's your turn. Thank you for watching and listening.